This is our final video for Chapter 3 of AP Statistics. Nothing too heavy today, just a few last-minute things to talk about as far as correlation, regression, etc., etc. Now, something to note, correlation versus regression. When you switch the x and y, it does not affect your r. It doesn't affect your correlation coefficient. But your least squares regression line will change. Okay? Also, be careful. Remember to not always trust your r as far as if it looks like a line or not. So, what I want you to do now, on your page you have 4 sets of data, A, B, C, and D. These are the scatter plots that go with them. I want you to pause this video right now, y'all, and I want you to plug in each of those data sets, and I want you to calculate 2 things. I want you to calculate R, your correlation coefficient, and I also want you to calculate your least squares regression equation, right? Your line of best fit. And I want you to see which of the following has the highest correlation. So pause this video right now and do that. Surprise, surprise! They all have the same correlation, which means you need to plot your data first to make sure that linear regression is in fact a reasonable tool. All right, something else to talk about, outliers and influential points. Surprisingly, not always the same thing. Correlation and regression are not resistant. Points that are outliers in the y direction, in the vertical direction, have a large residual. So you can see that right here, this point where my little cursor is, large residual. Points that are outliers in the x direction are often called influential because removing them dramatically changes the result. They tend to have smaller residuals. So, this same graph right here, cost versus battery life, here's your line of best fit with the outliers, and here it is without the outliers. Look what happens when you take away this extra stuff. It's amazing what can happen. So, a little bit more about outliers, okay? Outlier is an observation that lies outside the overall pattern. We already knew that. An observation is considered influential if removing it would really change the result of the calculation. So like I said, if it's an outlier in the x direction, in the horizontal direction, that's often influential. Now, please note, not all influential points are outliers, nor are all outliers influential points. So let's look at some more. Okay? The left graph, we have a perfectly linear situation. And the right graph, the last value was changed. So clearly influential because it changed the graph significantly. However, the residual is really small. Okay? So difference between outliers and influential. So let's do an example. This is on your notes. Scatterplot shows the payroll in millions of dollars. Wouldn't that be nice? And number of wins for Major League Baseball teams back in 2016, along with the least squares regression line. The points that are highlighted, so you can't see it on your paper because it's all black and white, but here, this is highlighted in red. The point highlighted in the far right is the LA Dodgers, and in the upper left is the Cleveland Indians. So what we want to do, describe what influence the point representing the LA Dodgers, this far right point, has on the equation. Explain your reasoning. Okay? What does that point do? Well, that value actually helps strengthen, or it helps or strengthens, I should say, the least squares regression equation because it follows the linear pattern. Right? It follows the linear pattern. It helps it out there. Now, our next question, what influence, or describe what influence the point representing the Cleveland Indians has on the standard deviation of the residuals and on R squared. Explain your reasoning. Yikes, what does that mean? Well, the Indians, right, Cleveland Indians, increase the sum of the standard deviation of the residuals, and it decreases my R squared, my coefficient of determination, because the value is far away from that least squares regression equation. Okay? So, read more about that in your book if you need some more help. And there's definitely more examples in the text as well. Now, some limitations. I've said this before, but I'm going to say it again. The distinction between explanatory and response is important in regression. It does not matter for correlation, but it does for regression. So it doesn't matter when you're calculating R, but it does matter when you have your equation of your line. Okay? So, for example, same data down here, okay, but they switched our explanatory and our response. Notice how R squared is the same, which means R would be the same. But our equation of our line of best fit, our least squares regression line, has changed. Still is a negative slope, but it's a different y-intercept and a different slope. So, be careful. Correlation and regression lines describe only linear relationships. This right here, don't do it. It's bad. So while we would love to have something that helps us with things that are not linear, we do not at this point in our lives. We will not in this course. Some other limitations. Again, I'll say it again. Correlation and least squares regression lines are not resistant. Outliers and influential points change things. Okay? They change things. You can see the change here when those outliers and influential points are removed. So another example of that. This is a picture from your book as well, so you can read more about it. So with all of the info, with all of the children, this, I don't know what you want to call it, blue? Sure, this middle blue line is our line of best fit. When we take out child 18, way down here, look what happens. Look how much the line has changed. It's no longer following that linear pattern. And you can see your R has gone from being moderately negative to, I'd say, a weak negative. Right? 0.33 is not very strong. When you take out 19, which is up here, it actually makes it stronger. Changes my slope. Keeps the same y-intercept, which is interesting, but it does change my slope, right? It's now steeper slope. Okay? So just realizing how these things change. Last thing that we're going to talk about. Association does not imply causation, y'all. Right? Even if it's a very strong association between an explanatory and a response, this is not by itself good evidence that shows that changes in X, actually cause changes in Y. Notice here, doesn't cause it. You can say there's a relationship, but you can't say that one caused the other. You have to be so careful. Even if it's a super strong correlation, right? Even if your R value is 0.99, I can't say for sure that one caused the other. Okay? So, for example, a serious study once found that people with 2 cars live longer than people with only 1 car. Owning 3 cars is even better, and so on. So, there is a substantial positive correlation between the number of cars, X, and the length of life, Y. So, does that mean owning more cars causes me to live longer? No. How come? There's this thing called a lurking variable. Okay? Lurking variables are these other hidden things that we didn't actually gather data on, but can affect it. So what might be the lurking variable here? Well, chances are if you have a lot of cars, you probably have a lot of money. If you have a lot of money, you probably take better care of yourself. You have more money for health care. You probably, actually care about yourself and your health and your body versus, you don't have a car, maybe you're unable to care for yourself as well. So, just because there is an association does not mean that one causes the next. All right, so that wraps up our chapter 3, Lots of things that we learned about correlation as well as regression. Lots of things to calculate in our calculator. Lots of things to interpret. So, do lots of practice problems. I didn't really specifically give any for this chapter because all of them are awesome. So, go through, do the practice problems, and yeah, have a great time with our correlation and regression.